Scientists just made a time crystal you can actually see with your own eyes. A real, moving, repeating pattern, visible under a microscope, and under the right conditions, this time crystal is even visible to the naked eye. And here's the thing nobody is talking about. This discovery is not what most people think it is. Of course, it's not a time machine or free energy or a portal. Well, nothing like that. But what it actually is might be far more interesting than all these things combined. In this video, I'm going to break down exactly what a time crystal is, why scientists could never see one before, how a team at the University of Colorado Boulder finally changed that, and what this could quietly do to everything from security technology to data storage. I'm also going to debunk the biggest misconceptions floating around right now, because as you know, the internet has already started running wild with this one. So, let's begin. You already know what a regular crystal looks like: salt, diamond, quartz. These materials have one thing in common. Their atoms are arranged in a pattern that repeats across space. You zoom in, you see a structure. You move over a little, you see the same structure again. That repetition is what makes it a crystal. A time crystal does something different. The repeating pattern is not across space, but it's across time. Here's the simplest way to say it. A normal crystal repeats from place to place. A time crystal repeats from moment to moment. The system keeps returning to a pattern over and over in a stable and organized way. Even when you disturb it, it bounces back. That is what makes it truly unusual. Think about ordinary systems. You stir a glass of water, it eventually goes still. You push a pendulum, it eventually slows down. Normal systems lose their energy and settle. But a time crystal keeps repeating its pattern in a way that resists the settlement. It maintains order through time. Now, the phrase time crystal sounds like something out of a Marvel movie. And that is exactly the problem. Because the moment people hear it, they imagine scientists holding a glowing gem that controls time. That is not this. This is about matter organizing itself, not about controlling time. But here is where it gets interesting. Even though the concept has been around for over a decade, nobody had ever actually watched one happen until now. The idea of a time crystal was first proposed in 2012 by Nobel laureate Frank Wilczek. His original concept actually ran into serious physics problems. It suggested a system could keep moving in its lowest energy state, essentially something for nothing, which does not work under the laws of physics as we understand them. That version proved impossible. But scientists kept pushing. They found a different approach. Instead of a system moving on its own, they built systems that were driven by a repeating external force, and those systems responded at a different rate than the driving force. That mismatch, that stubborn, organized response, became the signature of a time crystal. The experiments that followed were real. Trapped ions, diamond defects, ultra-cold atoms, quantum processors. Google's quantum computer was involved in one of the most talked about demonstrations. These were genuine scientific achievements, but there was a catch. You could not see any of them. To know a time crystal was there, scientists had to infer it. They had to run measurements, interpret quantum data, and look at graphs that showed the repeating behavior indirectly. There was no moment where a researcher looked through a lens and watched a time crystal doing its thing. That is the wall this new discovery just knocked down. This is where things start to get interesting. The team at the University of Colorado Boulder did not use quantum processors or ultra-cold atoms. They used liquid crystals. You already have a relationship with liquid crystals, even if you do not know it. The screen you are watching this on almost certainly uses liquid crystal technology. These materials exist in a strange middle state. They flow like a liquid, but their molecules have a kind of organized orientation like a solid. That combination makes them incredibly responsive to outside forces. Here's what the researchers did. They built glass cells, essentially thin chambers between two pieces of glass. The glass was coated with dye molecules. Inside those chambers, they placed liquid crystals made of rod-shaped molecules. Then they shined a specific kind of light onto the setup. The light did not just illuminate the material, it drove the material into motion. When the light hit the dye molecules, those molecules changed their orientation. That change squeezed the liquid crystals around them, and the liquid crystals responded by forming moving patterns, organized repeating patterns, patterns that kept going. The structures at the heart of this are called topological solutions, or kinks. Think of them not as individual atoms, but as stable twists or defects inside the liquid crystal. These kinks behave almost like particles. They move, they interact with each other, and when the conditions are right, they organize themselves into patterns that repeat over time. Those patterns can keep going for hours. They can cover areas larger than a square millimeter, and you can watch them happen through a microscope or in the right setup with your own eyes. Before you picture a glowing crystal sitting on a lab bench like something from science fiction prop department, let us be specific about what visible actually means here. You cannot hold this in your hand. It is not a gemstone. What you can see is the moving pattern inside the liquid crystal material, stripes, repeating structures, motion that organizes itself and keeps cycling. Under a microscope, that pattern is clear. Under special lighting conditions, it becomes visible even without magnification. That distinction matters because previous time crystals required scientists to infer everything. There was no pattern to watch. There were only measurements to interpret. Now there is something to observe directly. Researchers can watch how the patterns form, how it responds when you disturb it, how it recovers, how it changes when you adjust the light or the temperature. And that observability is not just a cool visual. It is a science. The patterns are also resilient. Even when the researchers introduced random disruptions varying the light in unpredictable ways, the time crystal recovered its ordered state. It did not collapse, it snapped back. The team could also tune the timing of the repeating pattern, stretching the period from milliseconds to tens of seconds just by adjusting light, intensity, and temperature. Here is where this gets practical. Researchers are not claiming this will change your phone tomorrow, but they do see real directions this could go. The first one is anti-counterfeiting. Imagine a banknote or a document that has a security feature built into its material. You shine a specific kind of light on it, and a unique moving pattern appears. Not a static hologram, a pattern that repeats in a specific way over time. That pattern is a time watermark. It is much harder to fake than something that just looks a certain way because you would have to replicate not just the appearance but the motion. The team also described more complex versions, stacked patterns they call time barcodes. Instead of a barcode that encodes information through lines in space, a time barcode encodes information through patterns that change in a specific way over time. That makes it exponentially harder to copy because the security feature is not just how it looks, but how it moves and when. None of this is in your hands yet, but the foundation just became visible for the first time. Time crystals were once a theoretical idea that seemed almost too strange to take seriously. Then they became real, but only inside quantum systems, so controlled and so hidden that most scientists could only interact with them through data. Now they exist in a material you can put under a microscope and watch. Each step makes the phenomenon more accessible, more controllable, and more useful as a receipt. When you can see something, you can study it differently. You can watch it fail. You can watch it recover. You can probe it from different angles and see what changes. The patterns in this experiment bridge multiple fields at once: material science, optics, non-equilibrium physics, liquid crystal technology, information systems. That kind of cross-disciplinary relevance is often a signal that something is worth paying attention to. The temporal period of the repeating pattern can be tuned across a wide range, not just by adjusting light and temperature. That tunability is what makes it a platform, not just a demonstration. Scientists now have a knob they can turn, and they can watch what happens when they do it. What do you think is more interesting? The fact that matter can organize itself through time, or the fact that scientists finally made it visible enough to watch? Let me know in the comments below. And subscribe for more informative, genuinely interesting videos like this one.